a novel regulatory layer within the plant circadian clock, and also in the fly, not deeply connected with the clock, but controlling the clock, which is a core or post-transcriptional event besides transcriptional and translational regulation. At least alternative splicing, we think, has an important place in the clock field. And this is apparently coming as a common theme in different organisms. In Drosophila, the PER gene. In Neurospora, the frequency gene is also alternative splice, and those splices are regulated by temperature, and the same thing happens in Drosophila. And now we have identified an important regulatory mechanism through alternative splicing of PRR9, and other groups have identified a role for alternative splicing of CCA1. So I'm going to finish with this. So a recent paper 2 years ago, or a year and a half, just appeared in the cover of Nature saying they cracked the splicing code. It was an ambitious title, probably very, very ambitious. When you read the paper, it was a great paper, but what they discovered is a way to predict whether the splicing outcome of a gene in different tissues, when the tissues were already developed. So it's kind of a static system where the tissues are already there, and you get a new gene, and you can predict using the information you get in a computational model which the splicing will take place. But there's something clearly missing in that picture, and if you are awake still, you can probably figure out. And it's missing the dynamic component. So the game needs a clock, and for alternative splicing to have some meaning, you need to have some change, some regulatory aspect in a dynamic context. So this is one of the things we are doing, besides trying to identify genes that regulate the clock and the flowering time, which is important. I think the circadian system is a good dynamic system to discover some rules governing some key basic cellular processes which are common in organisms and are present controlling the clock. So this is what we are trying to do, use the circadian system to figure out some rules of the splicing code, a dynamic system. So with that, I will stop and acknowledge and thank all the people working in my lab, which are over there, and they do a really hard job every day. Current members, Sabrina, Ana, Esteban, Matías, Gustavo Schlagen, Esteban Hernando, Soledad Pérez Santayo, some members that are not with us anymore, and some future members as a time talk. We have some future members joining us, and all our collaborators, the ones are on the first column, are from Argentina. Alberto Cornby, Ezequiel Petrillo, Fernanda Seriani, Pablo Sardán, Jorge Casar, Javier Boto, and the ones on the right side are international collaborators, and thanks to the agencies that support our work, National Agency, Howard Hughes, Guggenheim, Fundación Bungibor, Antorchas, University of Buenos Aires, and CONICET. With that, I end, and thanks a lot for listening to this.
Okay, we have time for 1 or 2 questions. Okay, I have one short question. Can you tell us a little bit more about the link for genes? Or
so we identified 12 genes that are regulated more by light at night than during daytime. And within those, there were CCA1 and Gigantia. And there were others that were homologs of CCA1. So they are not CCA1 or HY, but are related. There were 4 genes that they are unknown. They don't have any domain that you could identify. They are specific to the green lineage of evolution. And they are really clock controlled, strongly clock regulated and light regulated. And we don't have a clue. We know they are targets of TOC1 probably, but don't know what they target. And we are just figuring out.
Okay, thank you.